Welcome, students. In the last video, we talked about galvanic cells, and we looked at how to draw a galvanic cell using a salt bridge and electrodes connecting two different containers that had solution in it. So I'm going to build on that today, and we're going to actually talk about a standard reduction potential, or delta E. So we're going to talk about energy sub naught, delta E sub naught, and how to calculate it using half reactions. So before I do that, let's break this galvanic cell down here. So on this side here, we have our anode. And when we look at this, we have zinc. And what's happening here is the solid zinc on this bar are coming off and going into solution and forming zinc 2 plus aqueous. So the two electrons are flowing across here, going through this voltameter, going down into this copper electrode on the other side. So in this container here, we have some solution that has copper 2 plus aqueous. These ions, these cations, are attracted to these two electrons that are flowing down in here. So what they're going to do is they're going to come up and they're going to form solid copper and build onto this electrode all around it. They're going to build up. So what's happening on this side here is the zinc is diminishing and will end the reaction once the plate is gone. That is how a galvanic cell works. So when we look at this, this reaction is spontaneous. It is flowing from the anode to the cathode. When we have this disruption, that's gone, the reaction stops. So we talked about this salt bridge. This salt bridge here is really important. It keeps a balance of the charges. So inside this one here, we actually have sodium sulfate. So what does this salt bridge do? It doesn't allow the ions to back up. So on this side, what's happening is we have a buildup of SO4 minus. We have these copper cations plating and turning solid. So it's building up this negative charge in solution. If we allow that negative charge to continue to build up, the reaction would stop. So we have the sodium right here exiting this salt bridge and flowing into this solution to balance that negative charge. Now on this anode side, we have the zinc coming off of the zinc metal and forming aqueous ions. So we have a positive buildup over here. Once again, if you have the positive charge buildup, this is going to actually stop. So this salt bridge allows sulfate, SO4 2 minus ions, to enter the solution and balance that positive charge. So that allows this reaction to proceed spontaneously. So what I want to do is look at the half reactions and then calculate E sub naught, which is a standard reduction potential. So when we look at the reaction that we just looked at, we have the anode and we have the cathode. And the anode was the zinc solid reacting to form zinc 2 plus aqueous plus 2 electrons. Then we have our cathode, which is the copper 2 plus aqueous plus 2 electrons going to form copper solid. So you can look up standard reduction potential charts on the internet. It's in the index of your book. And what you want to do is you want to find what volts each half reaction can produce. This reaction must always end up positive. There is always a flow of electrons, so that means it is positive. It has to be positive. If it turns out to be negative, it will not run. You will not have a spontaneous reaction taking place. So when we get this graph out and we begin to look through it, we will find in that chart, zinc 2 plus 2 electrons form zinc solid. Well, when we look at what we have here, we have it in the opposite direction. So on the chart, it says the zinc solid going to zinc aqueous and 2 electrons is a negative 0.76 volts. Because our half reaction is switched, it's reversed, we now change the sign. So instead of the negative 0.76, it is plus 0.76 volts. So now let's look for the copper. So here we find it, look down the chart, it is copper 2 plus aqueous plus 2 electrons produce copper solid. And that in this book says plus 0.34 volts. So now we can add these two together. So we drop our volts and we have 1.10 volts, and this is a positive. So this will run spontaneously until the copper electrode plate is empty. So we have calculated our, it's called E sub naught equals, and that is the standard reduction potential. So now let's express this in what's called cell notation. So I'm going to write this here, cell notation. So how do you write this reaction, this galvanic cells, 2 half reactions as cell notation? So the process is always you write the anode on one side and then the cathode on the other. And you want to go from the solid on the outside, the aqueous, separate the reaction with 2 lines, and then the aqueous and then the solid. So when we look at the anode, the solid is the zinc. So I'm going to write this as zinc solid, and I put a line to separate it. Then I have zinc 2 plus aqueous, and I put 2 lines to separate the actual half reactions. Now I go to the aqueous. When I look at what that is, it's Cu2 plus aqueous, my line to separate, and Cu solid, copper solid. So this is written out right here is our cell notation. So our standard reduction potential, we calculated it today. We got our E sub naught as plus 1.10 volts. That's our standard reduction potential. And we learned to put together cell notation of our 2 half reactions in a galvanic cell. Next time, we'll look at another galvanic cell and calculate our standard reduction potential and also write the cell notation for that. Thank you for watching.